Okay, so for linear maps, we have introduced the idea of correspondences in linear maps, and there's some examples here that go through and verify all those properties. Um, and once we've introduced those properties and we know how to verify that a map is that we have this special kind of map, which is an isomorphism, which is linear and it's linear. Um, it's a linear map and it's one-to-one and onto. Now, it's going to turn out, we're going to say that two vector spaces are isomorphic if if there's an isomorphism between the two spaces. And um, isomorphisms are essentially characterize vector spaces that are identical. So one problem is to verify that a map is an isomorphism. But the second stage, which is what we want to sort of actually focus on, is the second thing is some of the consequences. Now, a special case of an isomorphism is an automorphism. So over here, H, which was a map from R2 to R2, H is an automorphism because it's an isomorphism. It's from one vector space to the same codomain equals domain. That's what distinguishes an isomorphism. Here could be between different spaces that aren't the same space, but an automorphism means self or same. Okay. And there's some important examples of automorphisms, basically linear transformations of vectors in the plane. There's a geometric aspect of rotations and other things. So automorphisms are important, like in graphics and stuff like that. Okay, so now here's some consequences of being an isomorphism. So let's look and see what some consequences. So let's say that there's an iso, if we say V1, V, V and W, V, is, what this means is V is isomorphic to W. That means that there is a map, say J from V to W, means there is a map from V to W, and that's linear and one-to-one and onto. So let's see what some consequences are. Let's see if we can see what does, we know every vector space has a zero vector, right? So that this map here has to map the zero vector J, the isomorphism J has to map the zero vector from V. This is the zero vector in V. It has to map it to something in W. Well, let's, because the map is linear, okay, we have that zero, the number zero times the zero vector equals the zero vector. So um, J of the zero vector has to equal J of zero times the zero vector, because those are really the same vector. Zero times any vector is going to equal that vector back. So the number zero just, I'm not, what am I doing? That's not true. The zero vector times any vector equals a zero vector. So if this was like R2C, you'd have 0, x, y equals 0, 0, because you'd multiply the 0. It would multiply all the components by 0. Okay, but then because the map is linear, this has to equal 0 times the image of 0, okay? And the same thing, oh, so, but then this is the number zero, and J of zero is the image of zero, right? Well, but no matter what vector this is, zero times that vector has to equal the zero vector in W, because the zero vector times any vector in W has to equal the zero vector in W. So therefore, the image of the zero vector in J has to equal the image has to equal the zero vector in W. So it maps the zero vector of one vector space to the zero vector of the other one. That's actually what this first, an isomorphism maps a zero vector to a zero vector. And here's the what we just went out. I tried to sort of say here. This little calculation here. Okay, so now here's these three conditions are equivalent. If I'm, this is what we've defined a linear map as. It preserves linear combinations, and from this it's equivalent this other form here in which you replace this form here with this one here, where the image of a sum is the sum of the images, and the images of a rescaled vector is the rescaled version of the image, and you can, and it works, extends to any linear combination with any number of vectors. Okay, that's that first sort of um, um, introduction. Here are some examples. Let's do some of, well, there's only 8 minutes left, but let's see if you can at least recover from all this stuff and do on page 322. I apologize for being so much talking today rather than problems. We just have to get the subject introduced. Okay, so let's look at this first problem here. Number 2 on 322. We have a map from P1 linear polynomials to R2. So what's the image here of the vector 3 minus 2x? Okay, find the image. So why don't you try that, see if you can write it out, and then in the next few minutes